Okay, let's continue our discussion on acids and bases. Today we will be discussing on what factors actually do affect the strength of an acid or a base. When we give an example, for example, if you have an acid described by this formula, which has a proton and also associated conjugate base, the dissociation looks like this. You have a proton that is released from the acid and also a conjugate base. So if this is the acid, we have the conjugate acid here, and we have a conjugate base. So in this discussion, what we will see would be what factors actually do affect the dissociation of the acid so that the equilibrium would be shifted mostly to the right side. That is actually the measure of the strength of the acid. The strength of the acid is affected by at least 4 factors which are described here. First, resonance effects. When we say resonance effects, once the conjugate base is formed, is that conjugate base, is it stabilized by a resonance? So it's referring to actually to the conjugate base. The conjugate base, is it resonance stabilized? That's what we are referring to. If that conjugate base is actually stabilized, that means this equilibrium is mostly shifted to the right. Therefore, the strength of the acid is higher. The other factor is inductive effect. If, for example, the conjugate base that is formed has a factor like electron withdrawing group, meaning a highly electronegative element to stabilize the conjugate base, that would be a very strong acid. So we'll demonstrate this by examples. So this is, for example, if you have electronegative atoms and how they are attached, how close they are, would be affecting, or it's called inductive effect. The third one is hybridization effect. Probably you might remember in our discussion of hybridization, mostly sp hybridized orbitals, atoms with sp hybridized orbitals are more electronegative. That means the conjugate base can be stabilized because that hybridized element would have a stabilizing effect. So it is sp3, sp2, sp. So the most electronegative would be one which has sp hybridization. That means that is more acidic. So something which contains sp hybridized orbital would have a stabilizing effect of the conjugate base. Therefore, it would be more acidic because it favors the dissociation of the acid. The other one is element effects. Element effects means where is that negative charge is on? Is it on carbon? Is it on nitrogen? Is it on oxygen? Is it on fluorine? Etc. So the more it is on the most electronegative atom, that means it is more stabilized. Therefore, the dissociation is much more favored. So I will discuss each one of them with examples that really shows you the particular effects, the resonance effects, inductive effects, hybridization effects, and element effects. We'll continue. Continuing our discussion on resonance effects, I will demonstrate this effect by some examples. If you just look at these 2 compounds, you have CH3CH2OH. That proton has a pKa of 16. And if you see CH3COOH, it has pKa of 4.8. Obviously, this is more acidic than this compound, based on the pKa values. But how they are differing in the resonance effects? Let's see this compound. If you just dissociate this, CH3, CH2, OH is in equilibrium, mostly like this, would be CH3, CH2O minus, meaning if it releases proton, this is what you would end up. That's the equilibrium for the acid dissociation of this compound. Basically, when you see this oxygen is carrying the negative charge. And that negative charge, or lone pair of electrons, cannot be resonance stabilized because there is no any pi bond that you can push those electrons and make a resonance stabilization. So the conjugate base that is formed as A minus, if you remember in previous section, this is not resonance stabilized, not resonance stabilized. There is no resonance for this. Therefore, the dissociation is not that much favored. It needs a very strong base to pull off that proton. Otherwise, this equilibrium is mainly actually shifted to the left and very small amount to the right. That is, the reason being the conjugate base that's formed cannot have a resonance. You cannot write a resonance structure. Let's see this one. If you just dissociate this, similarly what we did in the previous example, the equilibrium would shift like this, and that you would have CH3 COO minus plus H plus, the proton. If you see this, the conjugate base is this. The conjugate base, if you just look at it, there is a pi bond at carbon oxygen, and you can really draw a resonance that stabilizes. The more resonance you can draw, the more that conjugate base is stabilized. This is resonance stabilized, therefore the dissociation is highly favored. What does the resonance look like? If you write this, the resonance that can be drawn is, if you just push the electrons back to this can come out, and you have an alternative resonance structure. So this resonance stabilization makes this compound to be more acidic because that conjugate base has a resonance stabilization factor. Let's see another example. Between these two compounds, if you just look at these two compounds, this compound has a more acidic property, and pKa is 19. This is pKa of 50. So if you just look at this, why it would be more acidic, if you just refer to one of the protons here and release them as a proton, let's see what happens. So if you have CH3CO, CH3, there is a carbon there, the equilibrium looks like this and that. So if one of the protons is taken out, you have CO, CH3 plus H plus. So basically, if this happens, and as you see from the pKa value, this has pKa value of 19, that's pKa 15, obviously this is more acidic. The reason being, once the proton is pulled off, the conjugate base, which is this, is resonance stabilized because you can draw a resonance by just pushing this back and this can come out. So there is a resonance that looks like CH2 double bond C O minus and CH3. So this is the resonance between these two that stabilizes the conjugate base. Therefore, this species is more acidic than that. Why that doesn't have a resonance? Let's see. If you just do the equilibrium for this, is CH2, CH3, if you have a very strong base and you are just able to deprotonate, you have CH2 minus, CH2, CH3 plus H plus. Now this electrons cannot be pushed to this because this cannot, it will violate the loose structure and it would be more than octet. Therefore this doesn't have no resonance. So because it doesn't have resonance stabilized for the conjugate base, it is a weak acid. No resonance stabilization for the conjugate base. Therefore, in summary, any acid, organic acid, that you can draw or write a resonance structure for the conjugate base is more acidic than the one which you cannot have. So if something has a more resonance structures, that would be a more acidic one. As you see here, pKa for the alcohol is 16, pKa for the acetic acid, the acid is 4.8. Here for acetone, the pKa value is just 19, but this one has pKa 15 because the reason being this is resonance stabilized. That is not resonance stabilized. Resonance stabilized, relatively. So these are one of the factors when you discuss resonance effects. So do practice with compounds that have resonance stabilization for their conjugate base, and some they don't have a conjugate base stabilized by a resonance. We'll continue about inductive effects. The next discussion would be on inductive effects and how it affects the acidity strength of a compound. When we say inductive effects, it's an effect that is through a sigma bond. It's not through a pi bond, because a pi bond can't do a resonance. But a sigma effect, which is from inductive effect, is what kind of electronegative atom is next to the conjugate base. So let's see with these three examples. You have ethanol, you have trifluoroethanol, you have also still ethanol, but the fluorines are next to the oxygen. So if you just were qualitatively assessing this is the weakest acid. A is weakest, and this is the strongest. Why? We'll see what the inductive effects look like. This is between the two. If you just look at the dissociation of this CH3, CH2, OH, you have seen it in a previous example, it is not resonance stabilized. Therefore, it's a weak acid, as we have already found out for A. But the rest of the two would have inductive effects that makes them a better, stronger acid than, for example, A. So A is the weakest, C is the strongest, B is intermediate acidity. For example, this could be pKa 16, this is pKa 12, that should be pKa less than 12, maybe 6, 7. So what is the reason for that? It is an inductive effect. So always, as I told you, it's important that the conjugate base should be stabilized. So in this case, for example, the conjugate base is stabilized relative to this by the inductive effect of the fluorines on this carbon, even though they are much more distant from the oxygen with one more carbon. So if you just see the dissociation of that C fluorine, I will just write them in loose form so that it's becoming more clearer. OH. So it's in equilibrium with CF, F, F, C. So that is the dissociation for B. So if inductive effects work just by electron withdrawing effect or dipole moment through a sigma bond. If you just look at here, because this carbon is highly electropositive, because fluorine is a more electronegative atom, it takes away all the electron density from it. It will take away the electron density from it. It will take away all the electron density. That means this becomes a sigma positive. When this becomes more sigma positive, the next carbon also feels the effect of this carbon. That means it becomes more electropositive as well, because there would be an electron that would be withdrawn by the inductive effect. Therefore, this negative charge is more stabilized or remain as it is, very stabilized, because this next to it is a positive center. So that carbon also, the electron density would be taken away. Therefore, you have this as by inductive effect, this becomes more stabilized. So it's more acidic than this one. So it's relative to this conjugate base. This one is more stabilized by fluorine's inductive effect. So if you have touching an electronegative atom, they would cause an inductive effect of withdrawing the electrons. Therefore, they would create a positive center on carbon that more stabilizes this negative charge. But even much more pronounced effect would be if the inductive effect of the element comes very close to the oxygen center. If you just see in compound C, you have CH2, actually CH3, but fluorines are here in the next carbon, OH. This is how it looks like. So the conjugate base, as you see, the negative charge is very close to this carbon, but this carbon is affected by fluorine very significantly, taking away its dipole moment. So this is significantly electropositive. That means sigma plus. So the sigma plus is neutralizing the negative charge, which is generated by the dissociation. So this negative charge is very close to where the inductive effect happens. Therefore, this is more inductive effects because it's close to the reaction center, to the oxygen. This is one carbon far, that's why it's weaker acid. But this one is very close to that negative charge and stabilizing the negative charge. So the negative charge is more stabilized by inductive effect. The electron withdrawing effect of fluorine stabilizes this negative charge because it creates a more positive center next to the oxygen. So the inductive effect is much more felt when it is very close to the oxygen and it's in the next carbon. So this is the strongest acid. This is the next strong acid because it's one more carbon away, even though we have fluorines, which can cause a lot of inductive effect, but they are much more further away from the oxygen than in the third one, on the C. This one doesn't have even any electronegative atom that can pull by inductive effect some electron density. So in summary, inductive effect is effect of an electronegative atom on a compound by stabilizing the conjugate base through a sigma bond. It's not a resonance effect, but it is just a dipole moment that is just pulling the electron density. So it's also distance dependent, how far it is from the reaction center or from the oxygen. So you should always remember what is the element. Is it chlorine? Is it fluorine? Is it iodine? Is it bromine? So what electronegative atom is attached to that? So if this was, for example, CF3, Cl2, chlorine, OH, as you know, fluorine is more electronegative than chlorine. Therefore, if we call this compound D is weaker acid than this C, because what you see, the inductive effect is not as high as what fluorine does by inductive effect. Therefore, D is a weaker acid than C, but not as weak as B and A. This would be comparing C and D by inductive effect. So what element is causing the inductive effect is important. Is it more electronegative or more distant from the reaction center? Those are what you should remember in terms of inductive effect. It's affected by the electronegativity of the atom and also how far it is from the reaction center, especially oxygen, to stabilize the negative charge. So in the next discussion, we'll see hybridization effect. Okay, we'll be discussing hybridization effects, how it affects the strength of an acid, and relatively what factors that affect the dissociation for that proton is particularly dependent on the hybridization of the element at which that proton is particularly attached to. If you look at these protons here, one of them, the pK is 50, that's the weakest acid. Next one is, one of these protons have a pK of 44, and this one of these hydrogens have pK of 25. So the only difference these carbons have, here the hybridization of this carbon is sp3. When we say sp3, it's referring to this carbon or to that carbon. Here, this carbon or that carbon is sp2 hybridized. Remember to review hybridization. And if you just look at this carbon or that carbon, this is sp hybridized carbon. So as you see here, the S character by percentage is 25. S character for this one is 25%. So that means that carbon is not as such as electronegative as this one, because this carbon, one of this carbon have 33% S character. Because if you just have these three orbitals, divide 100 by 3 is 33%. If you have these four orbitals of the sp3 on carbon, 100 divided by 4, you have 25%. Here the S character is 50%. So as S character increases, the electronegativity of that atom increases. Therefore, this carbon can easily carry the negative charge when it dissociates into its conjugate base. What happens is, let's see, you have HC dissociating into, let's say, HCC plus H plus. Basically, what we are saying is this carbon being more electronegative, meaning more S character means more electronegative. So that carbon can accumulate or hold that negative charge very efficiently than maybe the other carbons. So this is 50% S character. That means the most electronegative. Therefore, the negative charge on the conjugate base is comfortably seated on this carbon. As compared to this is the next acidic one with 44 pKa. This is the weakest because S character is only 25%, so this carbon is not as electronegative as this one or the other one. So as a demonstration of further examples, if you just look at this hydrogens, any one of these hydrogens have a pK of close to 50 because they are on sp3 hybrid carbon. This is sp3 hybridized carbon where the hydrogens are, but here if you refer to this particular hydrogen, it is on sp2 carbon. That is sp2 hybridized carbon. So that means this has more S character than this one. Therefore, that proton is more acidic than this proton. So this is more acidic as compared to this is less acidic. Because the hybridization is such that the S character is lower than this one. Now let's see what elements effect is for in terms of strength of an acid. If you just look at these three examples, you have a pK of 15.7 for water, referring to that particular hydrogen, this hydrogen. And if you just look at ammonia, that hydrogen has a pK of 38. In methane, if you just refer to this hydrogen, to one of them, pK is 50. So if as a choice, if all of these are given and somebody asks you what the acidity of that proton would look like, qualitatively you can just base on what elements that hydrogen is attached to. For example, here the hydrogen is attached to oxygen, here on nitrogen, here on carbon. So based on this, you can say that oxygen being more electronegative as compared to nitrogen and most electronegative than carbon, it has such a pK value distribution. So most electronegative atom, the hydrogen that is attached directly to that would be most acidic. In this case, it's most acidic. And this is least acidic. So when you say an element effect, it means that the hydrogen is attached to whether it is a more electronegative atom or it's a more electropositive atom. Based on that evaluation, you can decide whether that compound is acidic or not. So relatively for water and for that hydrogen, usually hydrogens that are attached to oxygen, their pK values are around 16, 15.7, etc. For nitrogen, the hydrogens are pK value of 38, so they are weaker acid than a hydrogen that is attached to oxygen. In carbon, obviously, something which is attached to a carbon, especially on sp3 hybridized carbon, the pKa value is very large. That means the least acidic one. So elements effect is how electronegative the element is, one. Second, how large the atom is, so that the electronegative charge would be distributed on the surface of that negative conjugate acid base. For example, for hydrofluoric acid, pK is 3.2. In this case, it's not based on electronegativity scale, but how comfortably the negative charge would reside on the conjugate base. The strongest acid is hydroiodic acid. So if HI dissociates, it would be H plus and I minus, the conjugate base. So the conjugate base is I minus, meaning the electrons are on negative charge, are on iodine. That means iodine is large atom, the size is large, and the negative charge can be distributed over that large sized atom. In addition to that, the trend in this would show you how the bond distance between hydrogen and iodine, which can easily break into I minus and H plus. So it's not only the electronegativity in this scale, And this, it's just showing you what the element is differing in size. For example, here fluorine is the smallest, chlorine is the next one, bromine and iodine the largest atom here. So in terms of the atom property, it's not only electronegativity, but how easy would it be to break the bond. For example, the bond strength between hydrogen and fluorine is very high, so it cannot release its hydrogen very easily, and fluorine is very small and it doesn't carry the negative charge much easier. So the bond strength or the bond length between hydrogen and fluorine is very small or shorter. Here it's longer and it is easily can break it to give you H plus and I minus. So especially in the halogen family, the trend looks like a little bit confusing, but you should remember it is in a periodic trend from top: fluorine, chlorine, bromine, iodine. So the size increases downwards, so that as the size increases, the bond length also is longer, and it's easy to break to give you this dissociation. So don't be confused in terms of which one is the most acidic one. Would be hydroiodic acid with minus 10 pKa. So this is the most acidic, and this is the least acidic ones. So the trend is here dependent on the size of the bond length and how easy it is to break the bond between hydrogen and the iodine or the fluorine. So if you just consider them as HX, in this series, the bond strength or the bond length is the determinant factor in determining the acidity of the halogen family. But here in the organic compounds, as we see, what is the electronegative atom at the center? So it's oxygen, nitrogen, carbon. So if you just compare oxygen, nitrogen to carbon, the electronegativity decreases as we go down. So therefore, that hydrogen would be least acidic in methane. And also the next one would be in ammonia, which is this hydrogen with pKa 38, but this hydrogen has the most. So we are just putting a comparative idea or strength of the acid in this case. So with this, we'll continue next time with the general properties of bases and also some common acids as an example.